So thank you very much. I changed a little bit the title of my talk because I've been talking about deep learning for several years now, and it's many times one criticism I receive is that deep learning is cool. It's very fun to classify things, but we'll never get anything meaningful or physical for astronomy or for galaxy evolution. So today I want to kind of argue that there are things that we can learn from deep learning or for using these new AI techniques that possibly cannot be done without them. And I think there's a potential there. I won't start with an image of a galaxy. I will start with an image of the back of the eye. And this is because last week we went to visit Google to give a talk about our work. And then we met with several people there. And one guy told us this story about they had in the science department there, where they were analyzing back of the eye images to get some diseases, to have some automatic algorithms to identify diseases in the eye that were previously flagged by doctors. And it turned out that deep learning was very successful in determining where the disease and classifying the disease. But then the guys started to say, and they realized that in the header of the images there was much more information, such as the gender of the patient, something like that. And it turned out that deep learning could identify with 95% accuracy, given these images, if the patient was a man or a woman. And no doctor can do it, actually. Then, after that, they spent 6 months trying to figure out why and what the deep learning is picking up here. And they still don't know. So this is to tell you that there's some potential information there, hidden information, that it's not easy to understand or pick it up by our brains, but these algorithms are able to pick it up. And if you extrapolate this to physics, it means that these kind of neural networks are able to identify some kind of subtle or hidden traces of physical process in the data we typically have, which are multidimensional, and we struggle many times to find what are the tracer or the observable that we can use to track a given physical process. Let me illustrate this. So basically, what happens is we have we have seen several talks here, and trying to compare basically observations with theory or with simulations. And what we typically try to do is our simulations tell us about some physics that is going on when we make consistent evolution of galaxies. And once observers, the question we ask is, if we want to identify a given physical process of galaxy evolution, what will be the observables in my data that will link my observations to this physical process? And this is, we've heard several talks today about how to find this particular observable to link it to the physics. And normally this question is not so easy to answer, given that we have dimensional data, imaging, spectra, we have IFU, and then you need to find what are the observables or in all this multidimensional data that will link to a physical process. And if you can't find this process or in the data, then you want to answer, if yes, if there's an observable there, then do I see any evidence in the data for this physical process? And I believe this kind of analysis of deep learning in multidimensional observations can help into answering these questions. So take this as a proof of concept, and we started playing with this using this forward modeling approach that Greg described this morning, using numerical simulations, and you use the VLAN simulations that we heard about already. And basically, we focused on this compaction event or blue nugget phase that already Joanna described this morning, and others, and we'll hear more, I guess, later in the week. So this compaction event, you can see it here, or a blue nugget phase, you can see it here in one of these simulations, and it's basically defined by an increase of the gas central mass in the central parts of the galaxy. This is as a function of cosmic time from one of these galaxies. You see the mass here, so in blue you see the gas mass, in red the stellar mass, and in the central KPC, and in black you see the dark matter. And you see that in these simulations at least, galaxies go through this compaction event, which drives an increase of the gas mass in the central parts of the galaxy, which triggers then an increase of the stellar mass. So the galaxy, during this phase, becomes baryon-dominated at the center, then there's depletion over here, and you build a core, so you build a bulge. So, and this is how this compaction event is defined in the simulations when you have all the information and all the history of the galaxy. So basically, you can use these simulations to try to find or look for evidences of this process in the data we have. And so what you can do is basically say, okay, I see these phases in the galaxies, and so since in the simulations I have all the information, you can kind of divide galaxies or in three different phases. Let's say the ones which haven't gone yet through this phase, which I'll call pre-blue nugget phase, the ones which are in the peak of this gas inflow toward the centers, we will call blue nuggets, and the ones which are post-blue nuggets, so the event has already passed. And the game now is go to the observations over here, since of course you have only one snapshot of a given galaxy, you don't have all the full history, so you want to see where these guys over here that you observe with telescopes lie, if they lie in this track. Now, the way we do this is, as Greg described already, is by mapping or into the observed space, or to compare apples to apples, let's say. So from the cosmological simulation, we will use, we will produce images as they would have been observed, in our case, by HST, in 7 different filters. So we map the simulations into the observed space so that we have a fair comparison into that. And these are the typical images we got from these VILA simulations. These are H-band HST simulated images. We do this in 7 different filters. And for this, each of these galaxies, now we use the formation history, as I just told you, to label these images over here into these 3 particular classes. So the pre-blue nugget, the blue nugget, and the post-nugget that you see here. And so the advantage here now is that you are labeling exclusively on this physics, let's say, and this is your observables you have in the observed plane. So as you can see here, so there are differences over here, but it's not obvious to find any structural measurement in that particular case that will identify one of the other objects. So then the question you can ask is, I use a neural network over here, and are there any distinguishable features given the observations that are able to put these objects in different tracks, let's say, of evolution? And the answer is yes. So and I'm showing here one example of this. So on the right hand here, you have another simulation, VILA 30, in which you have, again, this kind of behavior with the increase in gas over here, then the depletion, and then the core building. And here what I'm showing is what you get from the output of a neural network when you plug in images, not obviously these images of galaxies at different stages over here, and then you classify each image in the simulation. And basically what you get here in blue is the probability of being a pre-blue nugget. I'm sorry about the colors, it's not very consistent, but this will be pre-blue nugget over here. This is the probability that the network says of being a blue nugget, and this is the probability of being a post-blue nugget. And you see that it kind of tracks rather well the evolution that you see over here. So this will decrease with the gas mass is decreasing over here, and then the probability of being post is increasing as you get out of the blue nugget phase. So we consider, so this is telling you that there's some information in the data that allows you to track this. I'm using here again 7 filters simultaneously of HST-like images. Now, you say it's kind of easy, but in fact this compaction event or this blue nugget event, I've shown you a couple of examples where it's very obvious to see, but in fact it's not so obvious in many simulations. Things are more complex sometimes, and here, for example, you have a lower mass galaxy for which you have several of these blue nugget phases and not so well defined, and it's not obvious from the simulation where to define these these boundaries, actually. It's a bit of noise here. And actually, I'm showing here a 2D plot, but it's actually done in 3D. But you see that even in these complex cases, it's, of course, much more noisy. But you see that the green, again, the green is the blue nugget. Again, I'm showing here the probability of the neural network based only on the images. It's kind of tracking this kind of behavior, even if it is complex cases. So it's picking up some information there. I think the most interesting part is that, in fact, you can actually start putting, and it comes back to my point of you have an image and you need to put it in a kind of sequence of evolution. And this, you can start putting constraints, as we do for mergers, for example, on the observability time scale of this process. And now if you take all the images from the simulations again, and you plot them here as a function, and the relative time, define the difference in time of observations relative to the compaction event of the blue nugget in terms of Hubble time, you see again that all objects that are classified as blue nugget are indeed in a window of plus minus 0.5 Hubble time. So you see that when you go to the data, you can say, if I observe a galaxy in this particular class, I know which is the time window since the event. And this is kind of giving you more information about, or putting some temporal information on the classification. So just note that you can go and apply this kind of same idea as Greg showed for other processes, and an obvious one is mergers. And I want to advertise this work of a PhD student who is finishing now in Paris and applying for jobs in the fall. And basically, the idea here is, again, we're using here large-scale simulations, the Orion AGN, which has already been presented here, and again, simulating mock images in 7 different filters, and using these neural networks to detect mergers and measure the merger stage in kind of the similar way that Greg already showed. And again, the right thing over here is that you can define a merger time scale, in which our case we define the merger time scale as a time t merge which is the time since or between the galaxy with the companion was like 4 effective radii away from the central, and the time it takes from going to this distance of 4 effective radii to the center to collapse with the central galaxy. And so we define this as a pre-merger phase. This is our time scale, and this is the post-merger phase is the same time since the merger event so we count the same amount of time there. And here we generated, using this process, 1 million mergers images from the Orion AGN in 7 filters as observed by HST. And you can follow here a merger sequence. So this will be the pre-merger defined in this particular metric. Then you have the merger event, and then this post-merger. And again, you can play the game of trying to, given this information that you have here, try to go to the data and identify when you are sensitive and put some observability time scale in the mergers. So I want to challenge the audience here, for example. So one thing that we did is, if you do this, of course, in the simulations, everything that you know that they are mergers. But in the real observations, you have projection effects. You have objects that are on top of the other, and in fact are no mergers. So in this, I'm showing some simulated galaxies, and some are projection effects, and some are real mergers among this population over here. So are you able to tell which ones are mergers or not? So this is, again, to illustrate that it's not an easy measurement, or to cope with a measurement that is able to distinguish both. And the answer is that these are projection effects, and these are real mergers. So the challenge is to go and disentangle from those. Just a note that standard parametric, like Gini's M20s, for example, that is standardly used for this, will completely fail into that. And you see this is the typical boundary that you use to select mergers. So everything above these guys, this line will be mergers. And you see that all these fake mergers or projection effects fall in this region over here. So if you use this boundary to identify mergers, all the projections will be classified as mergers. Of course, this is exaggerated because we have the same amount of projections than real mergers. In the real life, you will have less projections, so the effect will be less dramatic. But the point I want to make is that if you feed this into a deep learning network, this is basically, and you classify in 4 classes: no merger, fake merger, pre-merger, post-mergers. This is the real from the simulations. Let's say this is the prediction, and you need to look at this diagonal over here, and which means that correct classification, and you see how the deep learning is able to almost perfectly separate the fake mergers from the real mergers. And this is because, again, we are feeding the network without any a priori with 7 different bands, 7 different filters, and somehow the network, we think, and this is one of the questions of the point that you don't know what's happening, and I'll go back to that, but we think that the network is automatically doing a photometric redshift. And so since he had got the colors and also finding globally what are the features there, and so he can separate between fake or projection effects and real merges. Now, going back to the blue nugget business, now the next step that we want to do is obviously when you calibrate these observability timescales in the simulations, you want to go to the data and go to candles in that particular case and see if we find galaxies in these different classes. And the answer is yes. We found objects that the network found objects that are in the pre-blue nugget phase, post-blue nugget phase. You see there are some differences, not obvious sometimes, but we found galaxies in the different classes. I will come to what's the meaning of this, but one of the main results that we found is that now, once you classify these objects in different classes, again, green is blue nugget, red is post-blue nugget, and blue is pre-blue nugget, you can look at the mass fraction. So as a function of stellar mass, where are these guys found? And you see that as a function of different redshifts over here. So this is mass, this is number. These 3 panels show different redshift beams. You see that we find that there's a peak or a critical stellar mass where the abundance of blue nuggets, as defined by the simulations and found in the data, are more abundant. So basically, we see that these blue nuggets peak at a stellar mass of 10 to the 10, roughly, while above a given mass, you are mostly dominated by objects that went already through this phase. So then you can ask, since we put some observability timescales, you can say, do this sigma 1 SSFR plot that we already discussed this morning show we any evolution? Is really an evolutionary track over here. This again, so sigma 1 SSFR and different redshift beams, and color-coded again, so pre-blue nugget, post-blue nugget. And you see there's lots of scatter, and something that we are investigating by essentially, if you took the average, you see that galaxies which are in blue nugget roughly move into this plane, into that direction. So most of the objects that are over here, high sigma 1 and low SSFR, already went through this compaction event. Now, let me go at the end. So with this, again, I talked about this is proof of concept. There are many things that need to be understood. So I'm just trying to say that there's potential over here, but there's many things that can go wrong and probably need to be investigated. I'm only focusing here on 2 things. And one of the main questions is, so deep learning is you feed everything into that and it will output something. The good thing is that it takes into account all the information that is there in a multidimensional space, colors, everything that we measure. It can figure it out by itself, but we don't know what features it's picking up. And this is something that it's clearly a drawback, and we need to understand better. This is going on. And the other point is something I'm working on now, is, well, I don't believe the simulations because the simulations are wrong, or because there are many ad hoc problems, things that are put ad hoc there. So training with simulation doesn't make any sense. Can I take out anything from that exercise? So to answer the first questions, what features are being used, this is something that is very active research in the deep learning community. We still don't know, and we cannot figure it out easily what the network is doing. It goes back to the first example I showed you about the back of the eye. We don't know. There's something there, but we don't know. What you can do is kind of approximations and saying you have a classification over here in 3 classes, for example. You can ask the network which are the pixels that the network pick it up, or more important, in taking the decision. And you see here, this is what I'm showing here in different filters, in 3 filters, 3 infrared filters, and you see that it kind of makes sense. So the network decides on whether it's in a given phase on the pixels that are in the galaxy. So it's not based on the noise, and this is something that could happen. This can be used. It's not very informative, but it helps you debugging. At the beginning, I remember sometimes we realized that the pre-blue nugget phase, since it's happening at lower masses, where the network was using the noise. So you can figure it out and try to debug like this. You can go in a kind of indirect reasoning and say, is it using color, for example? So we did this simple exercise. Again, I'm showing the same plot here. So this is a function of cosmic time, the gas, the mass. So this comes from the simulation, this comes from the neural network. And you see over here that if you use 3 filters of HST, this is, you get this noisy behavior that more or less follow this. Now, if you increase to 7 filters, you see that the information is much cleaner. So it means that the network is taking advantage of the color. It's using information on color because it's linked to star formation rate. So it's picking up. And if now you go from HST, you go to the James Webb resolution, but again, only using 3 filters, you see that it becomes, again, cleaner. So it's picking up some spatial resolution information. So I'm going very fast to the second point here, that is how I make sure that it makes sense to train with simulation and go to the observations, or how I make sure that there's a match there. And then, because the problem is you make a network, you train a network to do something, and the network will only do that. And this is a major problem. So you train a network to identify cats and dogs, and you throw an image of a pig, it will try to fit it up into a cat or dog class. So, and these cats happen the same thing here. So I find this effect in the simulation, but now it turns out that the observations are completely different. It will still try to push it in my given class. So there are several techniques to do this, to try to cope with the uncertainty, the real intrinsic uncertainty of the networks. I'm just showing here one example which I find kind of interesting. I'm exploring, this is very preliminary, but basically you can use these networks, I'm going very fast, to these kind of new models which are kind of generative networks, which don't predict but generate data. So from that, you can get images over here, and basically you use a convolutional network to reduce this image to 2 numbers, which I don't enter into the details, but basically you can have here a sampled, a latent space, which basically represent all your data here, all the pixels over here in an optimal way in a 2-dimensional space. And from this 2-dimensional space, you will use a decoder to reconstruct the galaxy. And basically, you will find this optimal representation of the data by minimizing a difference between these 2 guys over here. So you want that the network that reconstructs the image is very close to that one. Now, if you do this for all candles galaxies, this is what you get in the latent space. So now, you represent all the images that we have in candles in one filter, in particular case, in 2 parameter space. And this is where all galaxies lie. Okay? So what's the meaning of this? Then you can, for example, color code this by tip. So the cool thing over here is that from every point over here, you can now go to the network and reconstruct a galaxy. Okay? Because every point here corresponds to a different galaxy. You do this in a grid, and this is what the network is picking up. You see that objects that lie over here are kind of compact and small, and objects that go into that direction start to be larger and more elongated over here. So the network is understanding. It's representing all the morphological information that we see in the real observations into a 2-dimensional space. Now, you can see this more by color coding with our typical measurements that we use for morphology. For example, if you take B over A, axis ratio, you see that the network is putting round objects in this particular region over here, while more elongated objects are here. You see that high exercic index, so ellipticals, lie in this narrow sequence, while as you go into that direction, the exercic index decreases, but also the size. So you are kind of compactifying, again, all the information in a 2-dimensional plane, and this allows you to visualize high-dimensional data. Why I'm showing this? Because I'm going back to the first idea of how I make sure that observations, at least from this morphological point of view, make sense or compare well with simulations. Now you can take this plane that is defined in candles and project into the same plane the Villa simulations or the numerical simulations and see if they cope more or less the same space. And this will be at least from when observed by HST. And you see that they kind of overlap reasonably well. They cope more or less the same space. You see that you have less large galaxies over here, so galaxies are more are smaller, but also because it stops at higher redshift. One funny thing that you see over here is that there's a lack of objects in here as compared to this thing. And if you look back into here, objects that are here are basically objects which are inclined into that direction. So these are objects that are more inclined like this. Objects below here are inclined to the other direction. So for some reason, in the Villa simulations, you lack of objects which are given inclination, which I don't know. But this is a typical information that you can see by just looking at 2 dimensions, and you have an overall view of the data. And I think I'll stop here because I've already over time. Thank you.
Please.
So there is something I don't understand in the classes used for the blue nuggets, because you're assuming that 100% of galaxies go through a blue nugget phase. So in the candles observation, there will be galaxies that do not go in a blue nugget phase, but will look like, pre or blue nuggets or post blue nugget phase. And actually, if you look at the classification function of mass, you have that all the massive galaxies look like post, and all the low mass galaxies look like blue nuggets, right? Because they're smaller. So how do you quantify the contamination by galaxies that do not go through a blue nugget phase?
This is a very good question, and I think it goes back to this idea of what I was saying at the beginning, that if you train the machines, and this is one of the main limitations, and those who are trying to understand with this. So if you train the machine to output a given class, it will always try to fit all objects into that particular class. So then you can measure, and I just try to highlight one way of measuring this, but there's another, what is hard to measure is the intrinsic error of the machine. So what you want to know is, put it in terms of cats and dogs. If I have a machine that classifies cats and dogs, and then I show an image of a horse, you want the machine to tell, okay, I can try to put it into these two classes, but this image doesn't look as the others. And this will answer your question, right? So, and this is the... Because you cannot define this from the simulations. So you cannot define a class of something that you don't know. What you can say... No, but you can say is how secure or how certain is the network that this class is in a particular... So you can measure an error. This is the way.
So this is really interesting work as well. I just have two small questions. So when it comes to mergers and then the blue nugget phase, those time periods are really small in those phases comparatively to when the galaxies, for instance, isolated or not in a blue nugget phase. So the first question is, how are you dealing with this class imbalance in sort of with respect to classifying galaxies in real observations? And then the second one is that it seemed a lot of the time your probabilities coming from the softmax were actually sort of in the range of around 70% and 30%. So I was wondering, what's the mean of the maximum softmax probability, which will determine your contamination over an entire data set? And how confident are you in that?
Yeah, so I will answer the second question because I already forgot the first one. But the second question is, so we measure the accuracy basically. So the range of probabilities goes from 0 to 1, but indeed the ones which are exactly at the limits is not the largest fraction. It peaks around 0.7. So we quantify the error rate by this. In the simulations you have both. So you have a training set, and we kept some as test state as you do in the standard approach. And so basically we got an agreement, an accuracy around 70, 80%, depending on the cut, again, you're using the softmax probability. Yeah, so in that particular, so in this particular approach, the imbalance was not so dramatic. So we tried several approaches. One is like doing what you can artificial data augmentation. So basically, you rotate and then you augment, you increase the number of images available. And we did it kind of in a weighting a little bit and augmenting more the classes which were less balanced, basically. But it was not a dramatic effect. Okay, let's thank Marc one more time.